In this video, we are going to solve particle equilibrium related problems involving pulleys. We are going to deal with only ideal pulleys. But what do ideal pulleys mean? Pulleys which are massless and which are frictionless are called ideal pulleys. And under these assumptions, the tension in the rope on one side of the pulley is same as tension in the rope on the other side of the pulley. So if this pulley P2 is an ideal pulley, then tension in the rope on this side is same as tension in the rope on this side of the pulley. And this whole system is in equilibrium when an external force of T is applied. So the tension in the rope would be T throughout the length of the rope. As you are aware, the first step in solving such problem is to draw an FBD, and in this case we are going to draw free body diagram of pulley P1, and in order to isolate this part from the rest of the system, we are going to cut the rope at this point, and at this point. Since the tension in the rope here and here is T, by cutting the ropes we shall expose tension force of T acting upwards at both these points and a force of 1500 Newton acting downwards. So our FBD of pulley P1 is going to look like this. Two forces of T are acting upwards, force of 1500 Newton is acting downwards. And now we can apply the equation of equilibrium, sigma Fy equal to 0. And this would mean 2T minus 1500 equal to 0. And therefore, 2T is equal to 1500, or T equals 750 newtons. So a force of only 750 Newton is required to balance this weight of 1500 Newton and keep the system in equilibrium. And in this case, the tension in the rope throughout its length would also be 750 Newton. Now let us turn to case 2, where the arrangement is slightly different. And in this case, we shall draw a FBD of pulley P1 again. And in order to isolate it from the rest of the system, we shall cut the ropes here, and in the process we shall be exposing the tension force T at this point and at these points too. And by cutting the rope here, we shall expose a force of 1500 Newton acting on the pulley in downward direction. So this is how the FBD of pulley P1 will look like. And by applying the equilibrium equation, sigma Fy equal to 0, we shall get an equation of 3T minus 1500 equal to 0, which would mean T is equal to 1500 over 3, or T is equal to 500 Newton. Now you can see that in this particular pulley arrangement, only a force of 500 Newton is required to balance a weight of 1500 Newton. So the mechanical advantage is 3 times and is better than what it was in the previous case. Now we turn to case 3, where the pulleys P3 and P1 are connected with a mechanical link, and therefore we shall draw free body diagram of the pulleys P3 and P1 combined. As you can see, an externally applied force is T, and these are all ideal pulleys. Therefore, the tension in the rope throughout its length would be the same, that is, it shall be T. And in order to isolate these two pulleys from the rest of the system, we shall cut the ropes at these 4 points and here too, and we shall expose tension forces T at each of these points and a force of 1500 Newton at this point. And our FBD would look like this. Since the system is in equilibrium, we shall apply the equation of equilibrium, sigma Fy equal to 0, which would mean 4t minus 1500 equal to 0, or t equals 1500 upon 4, and therefore T would be equal to 375 newtons. So the tension in the rope would be 375 newtons, and a force of only 375 newton would be required to balance the weight of 1500 newton. So that's our answer. In this problem, pulley C can roll over the cable ACB and is held in position with the help of another cable CAD, which is pulled by a force F at point D. The pulley C is also subjected to a load of 2000 Newton acting downwards, and we have to determine the force F required to keep the pulley C in equilibrium and also the tension in cable ACB. So it is evident that we have to first draw FBD of pulley C, and we isolate the pulley by cutting the ropes at this point, and this point, and by doing so we shall expose the tension force T at this point, tension force T at this point, because the tension in cable ACB is same throughout its length, and the cable DAC would have tension of F because it is subjected to a force F. So the FBD is going to look like this. It shows the three tension forces acting on the pulley due to the ropes and the load of 2000 Newton acting downwards. Now we can apply the equations of equilibrium in x and y directions. So the first equation of equilibrium is sigma Fx equal to 0. We add up x components of all the forces and set it to 0. T cos 30 is the x component of this force, minus T cos 50 is the x component of this force, and minus F cos 50 is the x component of this force, and this would simplify to F equal to this decimal number times T. This is our equation number 1. Now we apply the second equilibrium equation, which is sigma Fy equal to 0, and the y components of all the forces are T sin 30 in this case, T sin 50 for this force, and F sin 50 for this force, minus 2000 for this, and all the terms added together would be equal to 0. And this would simplify to this equation, which is equation number 2. Now we plug in the value of F from equation number 1 into equation number 2, and we get this equation, which will further simplify to T equal to 1305.41 newtons. And when we plug in the value of T into equation number 1, we get value of F equal to 453.37 newtons. By rounding off, we get T equal to 1305 newtons and F equal to 453 newtons. And that's our answer. So thanks for watching, and if you like the videos, please subscribe to the channel